Thank you very much, Bala. So let me start by thanking Bala for this his huge contribution in shaping and guiding the Indian community, and as a personal remark myself. And with this, let me also invite you to join us for this Cosmic Diwali. So my job is to sort of set the introductory sort of stage by giving you an overview of the gravitational wave observation of the binary neutron star system by LIGO and Virgo that triggered this huge explosion in the astronomy community in the last couple of months. So just to sort of make sure that we are on the same page, the existence of gravitational waves was predicted by Albert Einstein almost a century ago as part of his theory of gravity called the general theory of relativity. And gravitational waves can be thought of as freely propagating oscillations in the fabric of space-time, freely propagating oscillation in the geometry of space-time. So people describe gravitational waves as ripples in space-time. So after a century after they were predicted by Einstein, the LIGO observatories made the first direct detection of gravitational waves in 2015. Of course, there was a large body of very strong indirect evidence supporting the existence of gravitational waves by radio observations of binary pulsars for the last couple of decades, 3 decades or so. In September 2015, the LIGO observatories in the USA made the first direct observations of gravitational waves from merging black holes, which was repeated by a second observation of another pair of merging black holes in December 2015, and a third one earlier this year in January 2017 also. Then a couple of months ago, in August, the Virgo detector joined the data-taking run of LIGO. This is the Virgo detector in Pisa, very close to Galileo. And a fourth binary black hole observation was made in August, which was announced a couple of weeks ago, which was jointly detected by LIGO and Virgo. And these black hole observations are quite remarkable by themselves. These are essentially, they themselves sort of have a huge milestone, mark a huge milestone in the history of astronomy. These are the first detections of binary black holes that merge in the age of the universe. These are the first observations of stellar mass black holes, black holes that are collapsed by that formed by the collapse of massive stars that are much more massive than about 20 solar masses. Here is a cartoon of all the known black holes, known stellar mass black holes that we know of from the astronomy. The vertical axis here is the solar masses in units of the mass of the sun. All these black holes in purple are discovered by the X-ray observations in the last few decades. And if you look at them, all of them, the estimated masses of all of these X-ray the black holes in X-ray observations have less than 20 solar mass or so. While this is a new population of black holes that are being discovered by the LIGO and Virgo, and what is shown here is these two black holes. This is the first event. This is these two black holes of mass about 30 solar mass merged to form a much more massive black hole, about 60 solar mass, which is followed by a similar pattern in the other events also. So we are essentially starting to map a distribution of a new population of black holes in the universe to this completely new branch of astronomy. Apart from that, these observations provide us the first tests of Einstein's theory in the highly relativistic regime, including preliminary evidence of quasi-normal modes, which is discovered by Vishweshwara in the 70s. We are not quite there to probe the exact nature of quasi-normal modes, but we will be in that regime the next 10 years or so. Apart from that, all these large number of astrophysical sources merging black holes at different parts of the universe essentially incoherently adds up to produce a stochastic background of gravitational waves produced by all these merging black holes. And based on the estimated event rate of these merging black holes, we anticipate that a stochastic background of gravitational waves would be visible in the next decade or so by the advanced observatories. We don't know when exactly, but it's a very, very potential, very, very, very possible measurement. So what has happened in the last couple of months is a completely new discovery, which basically adds color to this whole sound, which is the first gravitational wave observation of a binary neutron star system. This was on LIGO on August 17th at about 12 o'clock Universal Time. The advanced LIGO and the advanced Virgo observatories jointly detected the first gravitational wave signal from emerging inspiraling binary neutron star system. This is codenamed GW170817, which is the date of the event. So what is shown here is a simple spectrogram of the data. Basically, this axis is the time, and the vertical axis the frequency. It's not quite a simple spectrogram, which is what is called a Q transform, but you can think of it as like a time frequency representation of the data. So you could clearly see that there is a chirping signal here, a signal that has an increasing, whose frequency is increasing as a function of time. This is the LIGO Livingston data, LIGO Hanford data. It is not quite visible in the Virgo detector, but even the non-detection in Virgo has contributed to a very accurate localization of the source, because the non-detection itself tells that something about the location of the source in the sky. So this is a way of a simple representation of the data, but the data analysis, the way of detecting binary neutron stars or black holes is not using such a simple technique. It just caused some bit of confusion recently in the literature. So this is detected. These signals are detected by data analysis pipelines that use a technique called match filtering, which essentially involves cross-correlating the data with theoretical models of the expected signals. And these are precisely the theoretical models that Bala has talked about, and Bala and colleagues worked out the last 30 years or so by painfully computing higher-order corrections by solving Einstein's equations systematically in a perturbative way. So they provide us a very accurate description of the dynamics of this binary at large separations as they spiral in over millions of years, while we see only the last 100 seconds or so of the system. And by comparing the data with theoretical templates, which essentially is a cross-correlation, and the technique is called match filtering, which again was pioneered by, huge contributions was made by Sanjeev Surender and colleagues at IUCAA. And this was detected with a signal-to-noise ratio of about 32, which is extremely loud, which is the loudest gravitational wave signal detected so far, which is primarily due to the closeness of the system, which is not in the time scale, not distances of billions of light years, but only of the order of hundreds of millions of light years. And this corresponds, we can say that this is a confident detection. So the false alarm rate associated with the statement is only less than 1 in 80,000 years, which essentially means that only much less than 1 in 80,000 years we expect a false alarm like this, a fake signal like this. Only once in 80,000 years, noise would produce a signal that could be mistaken as a signal like this. The gravitational detection is a very complex process because the detector could, in principle, be affected by a lot of environmental noises. And this sort of was followed up by a huge amount of resources and a large number of data available in the auxiliary instrumental channels that record information of the environmental disturbances as well as various noise artifacts in the various parts of the instruments. And we can conclusively state that no observed disturbances the environmental sensors could account for the signals. Interestingly, in one of the detectors, the LIGO Livingston, there was a small noise transient, what is called a glitch, which is a sub-second duration event that happened during the course of this 100th second of the signal. It's about 1 second prior to this, the end of the binary neutron star signal. These sort of noise transients are fairly common detectors because these are very complex instruments which are affected by environmental as well as various noise sources within the instruments. And there are systematic ways of analyzing and categorizing them. And unfortunately, this glitch happened to be during the time of the event itself. But note that this is a really sub-second glitch while we are sort of zooming in only the last 10 seconds of the actual signal. So what was done was to basically sort of technical gating, which is basically window out the data over this period of 1 second to basically cut out the whole period of data that is corrupted by this particular glitch. And basically, this data was removed so that this glitch is not affected in our data analysis pipelines. What really made the whole thing much more exciting is the discovery of a coincident gamma ray burst by the Fermi GBM monitor. So the source was localized to about 28 square degrees in the sky, which is a quite remarkable thing in the history of gravitational astronomy. But because if you remember, the first few binary black hole events were localized to a large patch in the sky, which is of the order of 1,000 square degree, something that astronomers would laugh at. But because of this large sensitivity, as well as the presence of the third detector, Virgo, in this case, this event was localized to a fairly very small patch in the sky in the standards of gravitational astronomy, about 30 square degrees. And there was an independent observation of a gamma ray burst by the Fermi GBM. And this is the localized patch by the Fermi, and they beautifully overlap. And this basically caused the whole hell broke loose. And half of the astronomers in the world essentially started following up this observation using of the order of 70 facilities, several including in India. So we will hear more about this astronomical side from the talk by Varun Palirao following my talk. So let me come back to the gravitational wave aspect of this discovery. So by comparing the data with theoretical templates of the expected signal using a technique called Bayesian inference, because we are always making this inference in the presence of data, in the presence of noisy data, so we can never measure absolute parameters. We can only make some probability statement about the parameters. So what we draw is a probability distribution, the posterior distribution of the parameters given the data and the signal model. And the best sort of, it turns out that the dynamics of the binary, as well as the gravitational waveforms, are predominantly determined by a particular combination of the two masses of the neutron star, which is called the chirp mass. And this can be estimated very precisely. It's about 1.1888 with some sub% precision, which you can estimate very remarkably. But this is not something that astronomers are interested in, or general scientists are interested in, because we are interested in the properties of this actual object that make this binary. And the measurement of the component masses is limited by correlations between the two masses, as well as the spin angular momenta of these objects, which essentially introduce higher order corrections in the gravitational waveform. So this could not be estimated as well as the chirp mass. And again, if you assume that the neutron stars can take arbitrary spin angular momenta, like very, very possibly very high spins, like dimensionless spins of less than 0.85, the estimates of the component mass range between 1.36 to 2.26 solar masses for the more massive neutron star, and 0.86 to 1.36 for the less massive object. And this itself is mostly within the observed mass range of neutron stars by other observations, just radio observations of double pulsars, single pulsars as well as double pulsars. And we have some understanding. So if you look at the spin measurements, how fast these neutron stars spin from radio observations, and assuming we have very precise measurements of the spin frequency of a large number of neutron stars, including some in double neutron stars. And if you assume some reasonable equations of state to describe the neutron star matter, this would translate to a much smaller spin for the neutron stars of the order of 0.05. So if you assume this, if you assume that the neutron stars are only weakly spinning, then this would, which is motivated by the radio observations, this would allow us to constrain the mass of these neutron stars much better to a range of 1.36 to 1.6, and for the primary, and 1.17 to 1.3 for the secondary. And what is shown here is the actual posterior distributions of the mass of the primary neutron star and the secondary neutron star. If you assume a very wide possible range of spins, a wide spin prior, these distributions are very wide, as shown in this red histograms. If you assume a very tight spin prior, then the distributions are much narrow, shown here. And this certainly is very, very closely consistent with the observed masses of double neutron stars through radio observations. This gives us a fair bit of confidence that what we are seeing is neutron stars. But in principle, these could be some extremely light black holes or more stranger objects, etc. So currently, this could not be ruled out with very high confidence, but some of the follow-up observations will be able to make this statements much more confidently. Another very interesting property that neutron stars has is that unlike black holes, they are made of some actual material, which means that during the last course of the inspiral, the star can get tidally deformed due to the gravitational force of the companion, just like the moon creates tides on the Earth. So this tidal deformation will have some imprint on the emitted gravitational waveform. For example, it would cause more energy to be lost in gravitational waves and make the inspiral faster, very slightly faster. So this allows us to basically constrain the property, the amount of tidal deformation from the observed gravitational wave signal. And in this sort of adiabatic approximation at large distances, the tidal deformation can be parameterized in terms of a parameter called the tidal deformability or tidal polarizability, which is basically the ratio for the experts, it is a ratio of the induced quadrupole moment to the external tidal field. It's just related to the tidal Lau number, which is even sort of mentioned in the context of Earth, etc. So what is shown here is the measured value, measured constraints on the tidal or the tidal polarizability or the tidal deformability of the two neutron stars, lambda1, the primary, and the lambda2 for the secondary. And the color shows the height or the probability, how likely they are. So we have a very strong evidence that the tidal deformation is less than of the order of 500 for the primary neutron star and about 2,000 for the secondary neutron stars. And this allows us to sort of constrain the properties of the nuclear matter, this equation of states that describe this dense nuclear matter. For example, more compact neutron stars would result in a smaller value of the tidal deformability, while less compact neutron stars would produce larger value of the tidal deformability. And we have very strong evidence suggesting that or less compact neutron stars are sort of ruled out by this sort of observation. And we will hear more about this from the talk by Sukant Bose following this. And so just to sort of summarize, this is sort of a full summary of all the inferred properties of this black hole, neutron star. I'm biased towards black holes still. So a few interesting numbers to note is the distance, the estimated distance are 40 megaparsec, which is about 130 light years, million light years. And this has been localized to a galaxy called NGC 4993. And the simultaneous measurement of the distance from the gravitational observation and the cosmological redshift from the electromagnetic observation of this galaxy allows us to make an independent measurement of the Hubble parameter, which determines the cosmic acceleration at this local universe. We will hear more about this in Artish Man's talk later today. And there are some very interesting constraints on the viewing angle of this system. This allows us to constrain possible jet models on the properties of GRB physics, etc. And we will hear more about this from KG Arun's talk later. And it's sort of also interesting to note that this is sort of the closest short gamma ray burst that has a measured distance. Sort of the first time we are seeing a gamma ray burst at such close distance. And this sort of even sort of makes people wonder that we might have missed several sort of very close gamma ray bursts because of this faintness and so on. And this has a number of implications in fundamental physics and astrophysics and cosmology. For example, the gamma ray signals arrived at the Earth about 1.7 seconds after the gravitational wave signal, to the peak of the gravitational wave signal. And there are, most of the GRB models predicts that there will be some time delay between the gravitational wave emission and the associated gamma ray emission, because the gravitational waves are produced by primarily the inspiral and the merger of these compact objects, while the gamma rays are produced by the interaction of the jet. Basically, this interaction, this disk of nuclear material that is produced by the tidal disruption of this neutron stars and so on. So this tidal disruption and the jet launch is expected to happen some time after the sort of merger of the neutron stars. So the fact that these two signals arrived near simultaneously tells us that gravitational waves must travel at the same speed as light. And they have traveled of the order of 130 million light years. So this allows us to constrain the speed of gravitational waves to a remarkable accuracy. So the ratio of the difference between the speed of gravitational waves and the speed of photons is constrained to 1 with an accuracy of the order of 10 to the minus 15. It also allows us to do a number of interesting tests on fundamental physics, such as violations of Lorentz invariance and tests of equivalence principle, etc. For example, one such very nice observation is the constraint of the Shapiro delay. So if there is a massive object, or it will curve the space-time, and if the light passes through this, it will take an extra amount of time because of the curvature of the space-time. And this has been observed in the case of light for several decades now. And according to Einstein's theory, the gravitational waves also must undergo the same amount of Shapiro delay, which we can constrain now. So when we have constrained the difference between the Shapiro delay observed by the light and the gravitational wave to be less than 10 to the minus 6. And this also has a very interesting constraints on the equation of state of dense nuclear matter, which we will hear more from Sugan's talk. And finally, this also has a number of very interesting implications in the astrophysics and cosmology. First, there's a very strong evidence supporting the hypothesis that the short gamma ray bursts are powered by mergers of double neutron stars. And it also it provides a number of constraints on the physics of GRBs, which we will hear from KG Arun's talk. From the fact that we have observed one double neutron star signal over a period of certain time, or time space-time volume, allows us to constrain the merger rate of double neutron stars in our local universe, which we can get some number. And this is consistent with the same observed from the radio observations of galactic double neutron stars. So we have observed several double neutron stars as radio sources in our own galaxy, and we have seen them spiraling in slowly over several decades, which will enable us to make predictions of the merger rate of double neutron stars in our own galaxy, which people have made these predictions over several last couple of decades, and this inferred rate is still consistent with this predicted rates. And very interestingly, this simultaneous observation of the gravitational wave and the electromagnetic wave have enabled us to do a completely different way of measuring the cosmological expansion, currently the Hubble constant. So this is relying on the idea that gravitational waves are self-calibrated standard sirens. This is analogous to the standard candles in astronomy. The fact that we have a very good description of the source. These are really simple sources, which can be very well described by Einstein's theory. And it enables us to measure the distance to the source, the luminosity distance to the source, to some precision, without relying on any external distance ladder. And in combination with the electromagnetic observation, which allows us to measure the cosmological redshift, allows us an independent measure of the Hubble parameter, which we will hear from Archishman Ghosh's talk later today. So that's all I want to say. This is sort of a summary of what we know about black holes and neutron stars right now. It's the same picture, all the X-ray black holes and all the LIGO black holes and all the neutron stars observed by radio observations, shown in this yellow, and the first observation of a double neutron star using gravitational waves, shown in the orange here. So it's a really exciting beginning of the multi-messenger astronomy triggered by gravitational observations, and I'm sure you will see really, really exciting discoveries in the next years. And you can already see a preliminary evidence of this by looking at the AstroPH listing of arXiv, which is being flooded by hundreds of papers in the last few days. Thank you very much. Ask a question.
So I noticed that the chirp mass is different from the sum of the two neutron star masses by almost 1 solar mass or more. What's happening to the extra mass?
No, the chirp mass is not a sum of the. It's not a total mass of the system.
Okay.
It is
so
a
what
combination
is the difference?
of the individual masses.
Yeah. So what precisely is a chirp mass?
It's m1 m2 divided by m1 plus m2 to the power 5/3 or something.
Okay.
It's not a. It turns out that the definition basically if you look at the post-Newtonian formula describing a signal,
okay,
the leading term happened to be determined by this particular combination of masses.
I see. Okay, thanks.
Very elementary question, either you or Bala, you could answer that. 24 hertz, what would be the orbital separation in terms of stellar radii? Very roughly, using Kepler's laws. I can't do it in my head.
Say hundreds, several hundreds.
Yeah. So that is very significant. I see. Okay, thank you.
I can do the Kepler's law calculation and send you later.
Hi, Ajit. I have a question. You talked about the chirp, but not the ring down.
Yes.
Can you make some comment on that?
Yes. So because these neutron stars are very light objects, their frequency, the frequency is inversely scaled with the mass of the system. So the inspiral basically stops at several hundred hertz, and the merger and ring down would happen at about a kilohertz. And the LIGO detectors are not as sensitive at this kilohertz to see the merger and ring down.
Hi, I have a question regarding the merger rate of the nuclear stars. So you told that we have already calculated the merger rate from radio astronomy observations. So how are you able to do this calculation from just observing one? I'm right. How are you able to calculate this merger rate from just one binary nuclear star observation using gravitational waves?
Yeah. So it's a good question, and the answer is a bit complicated. But essentially, the summary is that we know what is the distance reach of these observations. We know that LIGO detectors will be able to see this phenomena happening at a distance of about 70 megaparsecs or 80 megaparsecs, etc. So we have access to whatever phenomena happening in a certain local volume. And we know what is the duration of our data, what is the duration of our observation run. So we have we know our space-time volume of the observation. So the fact that we have observed once in that space-time volume, you can make an estimate of this rate. It's sort of 1 per that space-time volume. That is the simplest calculation, but you have to worry about several things like selection effects, mass distribution of neutron stars that are assumed, etc. Yeah, it is made assuming some mass function as well as some model of the selection function, etc.
The radiation of the gravitational waves. So, yeah. What really triggers the radiation of the gravitational waves at the time of the merger of the neutron stars? Is it the merger at the crust, or what is that exact dimension?
Gravitational waves or the gamma rays?
Gravitational waves.
Gravitational waves are produced by essentially the motion, the accelerated motion of these mass concentrations. So even during the inspiral, gravitational waves are produced. In fact, the observed gravitational waves are mostly from the inspiral, if not all, from the inspiral, because we don't have sensitivity to see the gravitational waves from the merger yet.
And what accounts for the milliseconds delay between the observations between the two LIGO observatories?
That's basically like the gravitational wave travel time, because if you come from certain sky location, it hits one observatory first, and it has to travel to hit other observatory. And the light travel time between the two observatories, the LIGO observatory is about 10 milliseconds, and between Virgo and LIGO is about 20 milliseconds. So all these are consistent.
Thanks.
Quick question here. On the data, I noticed that the Livingston data looked stronger than the Hanford. Is that understood? And also, the absence of signal from Virgo, how was that actually used to really improve your positional thing? It wasn't very clear to me.
Yeah. So, in this observational run, Livingston had a slightly better sensitivity as compared to Hanford due to technical reason. And secondly, even if they had the same sensitivity, depending on the sky location, it can be more visible in one detector and less visible in another, because they all have some antenna patterns which do not overlap. So you can always find a location where one is visible, another is not visible. Same thing applies for the non-detection in Virgo also. The fact that it is not very visible in Virgo tells us that it has to be in a location which is where Virgo is practically blind or less sensitive.
Just one next question. When you have neutron stars piling in so close, you expect severe tidal deformation of the neutron stars. To what extent does a gravitational wave signal permit you to study the amount of tidal deformation?
That is one shown in this tidal deformability. This is basically our constraints on the tidal deformation. So we have a upper limit. This is in fact, this is actually a posterior distribution of the tidal deformation of these objects. So we can say that very high tidal deformation is sort of ruled out.
Okay.
This analysis requires a lot of careful follow-up, because there are several subtleties in the analysis to be
Also, I
followed up.
noticed that there was a noise glitch, more sensitive detector, just before the coming in of the signal. Now, neutron stars are known to produce glitches, but I do not think that you would have an extremely sensitive deformation of the neutron star that can be detected by your detector.
No, this is known to be an instrumental.
It's confirmed
yes, because
completely
you can see the evidence of this in the other auxiliary channels. The frequency of this is very different from the signal and so on.
So we have Gurudat from our online attendees. He thanks Ajith and asks that is this the event occurred in our galaxy or in other one?
No. This is in a very distant galaxy. This is about 40 megaparsecs.
Okay.
Well, we have the galaxy also. It's NGC, whatever, 43, 49, something. I can't remember. We have identified the host galaxy, and that is basically what allows the redshift estimation and all the Hubble parameter and so on.
Okay. Hello.